All right, so good evening, friends from India or other Asian countries. Good afternoon to friends from Europe, and good morning to the speaker, Bhagwati, which is actually right now in the Bay Area in California. So it's really nice of him that he has kindly accepted our invitation. So many thanks from my team, Raj, Puspendra, Sakti, Soyam, Ajay, and so on. I'm really happy that you could join us to share your exciting work, what you mostly did with Professor Ramamurthy Ramesh during your postdoc. And I'm really looking forward to your lecture. So Bhagwati is a rising star in Indian science. He has just joined the Department of Materials Engineering at the Indian Institute of Science in Bangalore as an assistant professor. Currently, he is working on emerging memory technologies for the Internet of Things, known as IoT, and artificial intelligence. Before joining Indian Institute of Science, he worked as a principal research scientist at Western Digital San Jose in USA. In the year 2015, he obtained his doctorate degree in material science from the University of Cambridge in UK, and subsequently he joined a scientist position at Max Planck Institute for Solid State Research, Stuttgart in Germany. And in November 2016, he moved to the US and joined Professor Ramamurthy Ramesh's group at the University of California, Berkeley as a senior postdoctoral researcher. Dr. Prasad has published more than 30 research articles in highly reputed journals and filed more than 35 patents, including 30 US patents. Dr. Prasad will be talking about his recent research work on Beyond-CMOS computing, Spintronics, Ferroelectrics, and Magnetoelectrics. So just a small announcement that during the lecture, we don't take any questions. If you have some questions, then you can kindly write that in the chat box or raise your hand. At the end of the lecture, first we'll take a group photo, and then we'll have the question answer session. So with this, again, I'm delighted. I'm looking forward to the lecture. So Bhagwati, it's all yours. Thank you.
You can thank you. Yeah, thank you, Subhankar, for inviting me for this talk and for such a nice introduction. So shall I share my presentation now?
Yeah, please.
Yeah. Can you see it?
Yes.
Okay. Okay, so good afternoon or good evening all, depending upon the location. Some of you may be in Europe, so good afternoon. Today I'm going to talk about Beyond-CMOS computing, which basically includes Spintronics, Ferroelectrics, and Magnetoelectrics. So my talk would be covering technological aspects of these things. Basically, I will start with what is these technology, why we need the CMOS, Beyond-CMOS computing technology, how the market is driving in this direction at this moment, and how we can from being a scientist, being a researchers, how we can really be prepared for the next generations or upcoming technologies. So how we can prepare ourselves with that. Okay, so before I present my talk, let me acknowledge to the people with whom I have worked and with whom I have great interactions. So during my PhD, I worked with Professor Mark Blumeyer was my supervisors, and my co-supervisor was Professor Judith Driscoll. So and then I joined Max Planck Institute, and there I worked with Professor Jochen Menhardt. And then I moved to UC Berkeley, and I worked with Professor Ramamurthy Ramesh. So I thanks to them for giving me opportunity to work with them and see the facility that they have and learn a lot of things from their group and several other group members. And then I joined Western Digital. So some of you may have heard Tiffany Santos talk. So she was my colleague when I was working the Western Digital, and so I have done something similar what she was presenting on other day. So today I'm not discussing about this, but I'll give you the overview of how the different technologies like Beyond-CMOS computing technologies are coming up in the market. Okay, so we all have been witness how this semiconductor technology had changed our world. So this has been basically well sort of guided by the Morse scaling law. Morse has given a guidelines that in every 2 years, the number of the transistors in a chip would become double and the price will go half. And that has really give the sort of the roadmap for the semiconductor industry. And since till recently, till I would say 4 years back, that has very well followed by the industry. But now we have come to the node, the node size where further reduction is not much beneficial. So if you see here that the number of the companies who are working on the smaller nodes are decreasing. So in fact, now if you think about the 16 by 14 node size, only 4 companies are working, and now we're talking about 7 nanometers. Even Intel is talking about, or IBM is talking about 2 nanometers nodes. So these nodes are very difficult because the process cost is more, fab investment is more. And also the question is that is there any economical or even technological advantage to working with the sub 10 nanometers node? We may get the miniaturization of the devices, but in terms of the requirement that we are looking for, the process speeds, I think we have enough what we have. So we don't need to too much worry about that directions. So if you look your computers, there are two parts of it. One is the CMOS. This is what about the CMOS progress. Other is the memory part, which is like a storage and memory part, which is the equally important and essential for the computations. So let me talk about this. So this is how the memory looked like in your computers. It's 1980s, von Neumann architectures, and still valid. So this is how this is a pyramid of the memory hierarchy. So when you are close to the processor, which is called the on-chip memory, or basically your SRAM or DRAM, that process much faster. So the RAM that we have, that process quite fast, as close to as CPU. But the storage, that where we store our data, which is basically nowadays we use the SSD, or earlier we used to use the hard disk drive. These devices, the access time for the data from these devices is quite slow. It's like 1 milliseconds. And even if you're talking about tab, like this offline storage, that is 1 second. So it takes a lot of time to access the data. So there is a sort of some difference, a big difference in the access time, and that creates some sort of wall, basically, or gap, which is called the memory wall or the memory gap. So what is happening is that right now we are limited by the access time of the data from the storage. Okay, so how to improve that? That is where we have to really think about, if you want to improve the capacity and computational capability of your system, because you need to also have the access of data, especially when we are talking about AI and IoT, where we deal with the large volume of data. Okay, so as I just said, that we are now in the era of data, big data, where volume, variety, and velocity, that matters. So if you talk about volume, we would be really, surprised by these numbers. Today, we are creating 2 trillion gigabyte data every day, which is a huge amount of data we're creating. And it is predicted that in next 4 or 5 years, we would be creating 175 gigabyte data, which is 4x of now what we have now. And so the reason is that because in next few years, the 75% of the worldwide population that would be connected with internet. And so they would be creating various sort of data, varieties of data, which includes video, photos, audio recording, email messages, documents, and etc. So what is happening is that whenever we create some sort of data, for example, today we are recording this presentation, or we have been recording several things, we don't want to destroy those. It could possible that some of that will be never required, but we always want to keep them. So that means we are in the now in the era of where we want to store a lot of data, and also at the same time, as I'm presenting my presentation today, so we also concerned about how fast, how nicely this data, the what I'm talking about, that is presenting. So basically the velocity does matter here. So when a lot of devices would be connected with that, especially when we would be talking about IoT devices, Internet of Things, then this will matter a lot. So velocity would be a serious concern as data traffic is growing exponentially. And since we are going to be the era of IoT, Internet of Things, what we are going to see that there will be exponential growth of the connected object in our everyday life. And so it is expected that in next 8 to 10 years, the IoT devices would be increasing from 19 billions now to the 46 billions. So from this, what we can conclude that the next 10 years would be the decade of memory and storage rather than the processor. So the processor part, we are pretty much happy. We are more concerned now, memory and storage. Okay, so this is the era of big data. That means the Internet of Things. So we are our computational approach is now shifting from computational centric to the data centric applications, because we are talking about now different cloud services, data centers, platform like Facebook, Google, Twitters, Instagrams. So so that means there is more requirement of the data, and some of you might know that Amazon has this cloud services, which is pretty revenue driven revenue generations for the Amazon, because that is where the business is all about. So on the one hand, we are using a lot of data. On the other hand, the concern is that how we can use this the data with low energy, because we are consuming lots of energy. In fact, the 50% of the energy consumption is by just used for cooling the data centers. So it is expected that, or it is now estimated that 3 to 7% of the global electrical energy is consumed by the computing devices. And if we don't do anything in terms of energy consumptions, if we don't make our devices more energy efficient, so maybe in next 10 to 15 years, the 25 to 30% of the energy that we produce would be consumed by the IT devices, and that would be significant. Like we would be needed significant amount of energy than what we require now. So that is a big concern, that how we can really make the energy efficient devices. And the third and most important concern for handling the large amount of data is that how we reduce the memory gap that just I discussed. Okay, so what we need a memory which perform like a DRAM or SRAM. So that means the DRAM and SRAM are close to the processors, and the access time for the DRAM and SRAM is like 1 to 10 nanoseconds, which is what our processor is also have the same access time. And so we want the non-volatile nature of the flash, which is DRAM and SRAM doesn't have, they don't have. And then we want to reduce the cost, so cost of the DRAM or NOR flash. So that means we want to make something called a universal memory, which is basically which solve all the problems, which can use as a storage as well as the memory, which is a non-volatile nature, and which also doesn't cost that much. Okay, so as we just discussed that why memory and storage technology is required, why we need a disruption in this field. So what we see that this is our current von Neumann architecture memory part. So here is your processors, which is we have a SRAM and DRAM here. You see that the speed of these memories is less than 10 nanoseconds. When you're talking about this storage part, the local storage or even remote storage, the access time is much larger, like in milliseconds range. So what happened is that over the years, the performance of the microprocessors has improved a lot, but memory couldn't make the pace with that. So I would say that there is a performance gap between that. And so as we are talking about the future need, where we are handling a lot of data, like we are synthesizing tons of data for different AI computations. So we need a memory which can basically respond. Yeah.
Bhagwati, I think we lost for several seconds. Could you explain this slide again, please? I think your internet is a little bit unstable.
Oh, sorry. Am I audible now?
Yeah, now it's fine. Please, maybe you can explain it again. Yeah.
Okay. What about the last slide? Did you hear the last slide?
No, that was fine. This slide also we heard a little bit, but yeah, it would be cool.
Okay. Yeah, sorry. The place where I'm living, maybe they don't have great internet, so I can just blame it to them. Okay. So what I'm talking about is that over the years, what happened is that we see that the microprocessors improve, like performance of the microprocessor increased dramatically, in fact, exponentially, but memory could not make the pace with that. So there is a performance gap between the microprocessor and memory. So this is memory is lagging behind the microprocessor. And now, if you talk about our future need, when we're talking about AI-driven, technology computations, where we would be working on data. So AI means somewhere we are handling a lot of data, right? So that means you need large amount of excess of data, and that should be also fast. So eventually we need this memory to be responding as fast as our microprocessors. And similarly for IoT devices, for example, it is predicted that soon, like maybe in next 8 to 10 years, we would be having our smart offices, smart kitchens, so where we can basically, you don't need to be at home, you just cook your food from your office and you can watch it, because we all already seeing these things now happening. And when you will be going home, the food will be ready for you. But all these things would require a lot of data traffic, like data minings and synthesis, and that all needed your fast computations for that. So this is the memory part. Other is a storage part. Right now we're storing a lot of data in different cloud centers, and those data centers they consume lots of powers, and because you also need to keep the multiple copy of the data. So that means the data storage is going to become also a big concern, because we're generating huge amount of data. So what would be the future storage sort of devices? Are we relying on the conventional data storage technology, or we need something called the DNA storage or optical storage, where we can store huge amount of data in a small volume? So we need some more innovations on that directions to how to make the energy efficient and condensed data storage systems. Okay, so probably some of you have been working and have been hearing about several emerging memory technologies. So we have been hearing about the FERAM and MRAM, or resistive RAM, or phase sense memory, and several others like ferroelectric memories and all. So what we see that these all memory, whatever people are working around, either they are in the research stage, or some of them are in the industrial, the pilot plant scale. Some of them are like early stage of commercializations. But all of these memory technology, they have some role to play in this hierarchy, in this pyramid. So if you see here is that when you're talking about SRAM or DRAM, which need to be faster, for example, SRAM need to be faster, but it can be size, in terms of size, it could be big. So for that, you can use the SOT, spin orbit torque based MRAM, which is basically two terminal SOT devices. So because if you make a two terminal, when you're talking about two transistors, it's a two transistor devices, basically it's a three terminal device. So it is a bigger device. And so, but it responds much faster, and also the energy consumption is lower. If you're talking about 1T, 1 MTJ, which is basically STT-MRAM, that can cater the need of DRAM, basically. And other concept, the voltage control magnetic anisotropy, that can also cater the need of your DRAM. So there are several other memory technologies. So what I'm trying to say here is that whatever people are doing in this space, there are a lot of things is going on in this space, and in this memory space, and people are targeting certain requirements in the memory hierarchy. So we need to see where our whatever, if you are interested in this memory technology business, where our research can fit, what kind of like what kind of application it may have at the end. And there is a huge requirement for having a new or emerging memory technology. So this is a recent so I have taken this from one of the conference. VLSI conference happened last year in San Francisco. In that conference, if you see that the 40% of the topic were presented on the ferroelectric parts. So, and this is a lot of people from the industry as well. So it indicates that a lot of things is going on the ferroelectric parts, because it's an emerging memory technology. Since this people have discovered the ferroelectricity in hapnia and doped hapnia systems, and because the hapnia is already known for the industry people, and people have been using it. So there is a know-how how you grow it for on the larger scale for technology purposes. So people are excited with this. If you can use this for some applications, then it will be easy to to basically make the devices and make the technology out of that. On the other hand, if you look the STT-MRAM, 21% people have presented STT-MRAM because it's relatively much mature than other technology. People are now very excited that some sooner or later some technology will come out of that, which will be soon. It will be part of our computation systems. You will be seeing this STT-MRAM based system, some sort of memory chip in your computers. So a lot of work is going on these directions. Okay, and then other things are like SOT-MRAM, which is spin orbit torque MRAM, then phase sense memory, and then resistive RAM. So they are like, some of them are already been a lot of work has been done, so people are not getting much hope from that, and other are like, okay, like people like new things and just trying what's going on in that space. Okay, so I have been working on Ferroelectric RAM and STT-MRAM over the last 8-10 years, and I have working on the in academia as well as industry. So this is the recently, like I was in Western Digital for 3 years. There we have worked on various FE-RAM and STT-MRAM based technology. We have filed several patents, and if some of you are interested to know more on the technological aspects of these devices, please read these patents, and you will learn how one can make the devices and crossbar kind of structure with that, and how these new things are coming in this space. Okay, so let me little bit tell you about the global memory market. So if you see here is that right now we are having around 115 billion, or maybe even little more now, in fact. So maybe somewhere around $120 billion market, and so it is projected that it's going to increase by with the to $180 billion by 2027. So what we see here is that various aspects of these memory technology. One is the semiconductor memory, other is the emerging memory technology. So if you look about the non-volatile memory market, that's also increasing with the rate of 12.47%. And now if you see in terms of the next generation memory, which is basically emerging memory technology, you see that the market of that is increasing from $3 billion to the $20 billion. So highest like the rate is a 25.4%. So there we are going to see huge requirement in the future. So what I'm trying to say from this presentation, this slide, is that there is a huge demand is going to happen in this emerging memory technology in the future. So there's a requirement, and there is also a scope for us to do some great technological work in this direction, the research and technological work. Okay, now let me come to the outline of my talk. So with that background, I'm now going to talk about Spintronics, which is mostly focused. I will be mostly focusing on spin filter tunnel devices. Then I'll be talking about Ferroelectrics, which is basically again ferroelectric tunnel devices. And so main focus of these things is how we can use these devices for memory applications. And then I'll combine these two things together, which is basically Spintronics and Ferroelectrics together, magnetic and ferroelectric together. Then that is called the Magnetoelectrics. So then I'll be talking about the work that we have done recently with Intel, how one can switch the magnetic systems or magnetisms by electric field, and the purpose is that how we can reduce the energy consumption. As I already spoken in the motivational slides, that the energy consumption is very important right now, how we can make the energy efficient devices. Okay, so let's now come to the Spintronic devices part. Some of you have already heard Tiffany Santos talk recently. She has spoken nicely about this topic, but let me a little bit also give you some background. So I would say the device elements of the Spintronic devices as of now is something called magnetic tunnel junction. Okay, in a magnetic tunnel junction, what we do is there are two ferromagnetic metals, and they are separated by a thin non-magnetic insulator, basically, which act as a tunnel barriers. Okay, so depending upon the magnetic polarities or magnetic orientation of these two layers, these magnetic layers, you may have a low resistance state and high resistance state. Okay, and this concept has been used in the read head of the hard disk drive, and this has been there for almost more than than 15 years now. Okay, it's a very well established technology. This is one of the like I would say successful applications of the spintronic devices, and it's widely being used everywhere. Okay, now, so this is about the read part. What our MRAM is doing, MTJ is doing here is that it's reading the information that you store in the this disk, which is a magnetic disk, which has several magnetic grains, and then you store the information in the magnetic grains, and this read head is read informations which is written in on those grains. Now, can we use this concept, this magnetic tunnel junction structure for writing the informations? That means, can we store it? So for that, we need to make a device where we can flip these magnets. Okay, we can flip these magnets easily and without and locally also, because if you want to make a dense memory, you need to have a localized you need to have a control in each and every device, and you can locally individually manipulate their magnetic states. So in earlier this people have tried to create some local magnetic field, and that was basically called a toggle MRAM, where yeah, it did work, but it is difficult to really make the high density memory with that. So the recently, or it's not recently, it's almost more than 10 years now, the concept came called spin transfer torque. So current driven switching, basically what happened here is that when you flow the current, unpolarized current, through a ferromagnetic metal, so what happened is that when you flow the current through the ferromagnetic metal, it gets spin polarized. Okay, and then these electrons, they tunnel through the thin insulator barrier, and then they basically, when they interact with the electron of other ferromagnetic system metal here, like electrode here, that can transfer the spin angular momentum. And according to, depending upon which way you flow the current, you can basically manipulate the magnetic state of this free layer, this ferromagnetic layer, to one way or other, basically make them parallel or anti-parallel, and that way you can basically manipulate the state. So this is very nice concept, and one can really make the density very dense devices and put them very close, so you can have high density memory device with that. Okay, now what we need here, so what we actually looking for here is that we need to create the highly spin polarized current through this ferromagnetic metal, so that your current is highly spin polarized, and you basically have the effective spin angular momentum transfer to this other layer. Okay, so what you typically, we use the ferromagnetic metal for this, like iron, cobalt, nickel, and the spin polarization of these systems is around 50 to 60%. Okay, so if you want to have more effective and highly effective spin angular momentum, because eventually what you need to if you want to transfer this spin angular momentum effectively, that means if you can reduce the switching current. Okay, this is what is the now sort of issue and sort of one of the bottleneck in the STT MRAM is that how to reduce the switching current. Okay, so one of the way to do is that if you can generate the highly spin polarized current here, and so can you do that by other means? Okay, so one of the mean is something called a spin filter, where you basically filter the one direction of spin and only allow the direction of spin to pass through. So how it works, let me little bit explain from this illustration. So what is happening is that if you have a normal metal and you fly electric field across it, what happen is that both, like irrespective of the spin orientation of the electrons, they will basically accelerate toward the positive bias. But now if you just imagine a situation where you have some sort of filter that allow only one direction of the spin of electron to pass through and completely block the other direction, then in these sides you can have the highly spin polarized current. Okay, so aim is to get the 100% spin polarized current on this side. Question is that how you can achieve these things. This looks interesting, but can you do this in the real world? Can you really block and can you filter the spin of the electron? Yes, you can do it. And there is an interesting concept where you basically introduce thin ferromagnetic insulators, which basically act as a barrier between the two metallic electrodes. Then you can basically achieve this. So how it works is that you have a ferromagnetic systems where there is a spin split basically at the Fermi level. So if you have an insulator or semiconductor, you have both valence band and conduction band, they have exchange splitting. Okay, so if you have a conduction band has exchange splitting, then what will happen is that the barrier heights for the so when you take this system as a tunnel junction. Okay, so for tunnel junction, what is important? The barrier height and thickness of the barrier. So if you assume that your barriers for the two different direction of a spin of electron is not same, then in that situation, what will happen is that, as we know, the current, the current density in current, that is exponentially depending upon the barrier height. So if you have two different barrier heights for two different direction of a spin of electron, then what will happen is that if then you will see that the current on this side would be mostly would be mostly having the spin orientation, or the electron which will tunnel through and come on this side would be having mostly the spin orientations of the barrier height, which is lower. Okay, so basically that way you can generate the highly spin polarized current. So even if you have a small separation between the barrier heights for these two, you can see the large difference here because it's exponentially dependent. Okay, so what you need for this kind of device, you need a material which is a ferromagnetic and as well as insulating. Seems a little weird and rare combinations that you see in the nature, but there are some. Okay, so European chalcogenide system, which is Tiffany Santosh supervisors, Professor Jagdish Mudira from MIT has investigated a lot, and these systems perform really well, but you need a certain R to grow these material systems. It's not straightforward, and also the temperature, the Curie temperature of these material system is lower. Other system, other spin filter or ferromagnetic insulator system is the gadolinium nitrides or dysprosium nitrides. These nitride systems has been worked by Mark Blumeyer's group, my supervisors groups, and they from Cambridge. And so, but these materials are also very tricky to grow. You have to encapsulate them. They have low TC and same issue. So other set of materials called ferrites, they have a higher TC. People have grown them, but these materials have their own issue because they are spinel structures, and when you want to grow them on some sort of electrodes, typically perovskite systems are electrodes, like you want to grow oxide systems. So at the interface, you create some sort of defects, and which reduce the spin polarizations, especially when you want to see the room temperature applications. Okay, so what about ferromagnetic insulating magnetites? Because the magnetites has a similar structures, like because they are perovskite, so there are a lot of perovskite systems that has that are conducting nature. So you have a conducting perovskite electrodes. On the top of that you can put them, and then they are simpler system to grow compared to ferrites, and you don't need to worry about any exposures, any sort of damaging of the films when you expose that those films in the air. So it's quite robust system. So I have used samarium strontium magnesium oxide, which is a magnetite systems, and this is the phase diagram of this material system. So what you see here is that in the low dope regimes, when you're talking about below 0.3, then this is actually ferromagnetic insulating systems. So somewhere around 0.25, you have a basically quite, you have ferromagnetic insulating phase, single phase here. And so this is what I have used, samarium 0.75 strontium 0.25 MnO3, which is basically so SSMO, we can say from here onward. So this is the particular ferromagnetic insulating phase that I have used for our devices. Okay, so we grow the films by PLD, pulse laser deposition techniques. Most of you might know this, how PLD works. So basically you have a rotating target inside a vacuum chamber, then you ablate the target materials by some focused laser beam, and if you have some background gas, then you basically create some sort of plasma plume that propagate and condenses on a heated substrate, and that's how you grow the films. So typically we use the single crystalline substrate. S2 is commonly used, which basically, and then you grow the films, and S2 typically have some sort of step and terraces morphology. If you grow the films which follow the same one, that means you are growing good quality films, and you basically want to grow layer by layer, like nice 2D growth. Okay, so I have used lanthanum nickelate as a bottom electrode. Okay, and that also lanthanum strontium magnesium oxide or lanthanum calcium magnesium oxide. So these are the bottom electrode, and samarium strontium magnesium oxide. SMO is my ferromagnetic insulating barrier layer. Okay, now let's come to the devices. So once we grow the films, we fabricate the devices. So this is a substrate, then we use the bottom and top electrode, lanthanum nickelate, and then SSMO is a ferromagnetic insulator barrier we have. Okay, so this then we use the hall bar pattern for optical photolithography, and that's how it looked like after photolithography and ion milling. So you see the series of 4 micron tracks here. Okay, and then here you can make your one device. Okay, so you can make around 14-15 devices in one chip, and then you further narrow down those tracks from 4 micron to like 500 nanometers by focused ion beam nanomachining technique. Okay, and then you rotate the sample, and then you can cut from the side like that. Okay, and then you can make devices. So at the end, that's how it will like. This is cross-sectional ACM. What you see here is that this is the top and bottom is a lanthanum nuclide. There's a thin black dot here, which is basically the barrier SSMO, and this is the gold top gold, which is sort of contact for making some wire bond contact, and also it protect our sample wire during the fabrication process. Okay, so what will happen? So we basically apply the current from the 2 electrode pads and then measure the voltage, which is basically a voltage is coming through. So the current is passing through here. So this is the voltage that we are measuring, is a voltage drop across here. Okay, so that means since you have the gold and lanthanum nuclide are metal, so whatever the voltage drop that we see, that significantly is coming from the one which is dropping across the barrier here. Okay, so let's now see the transport data. So this is the R versus T of the films, SSMO films. What you see is insulating nature. Okay, so we measure these devices all the way down to 5 Kelvin, but it's so insulating that below 175 K we could not measure it. Okay, so I did measure all the way down to 5 Kelvin, so make sure that there is no metal to insulator transition is happening at low temperature. And this is the R versus T of lanthanum nuclide, which we use as a metal, as electrode, which showing the metallic behavior. And now when you measure the R versus T of a device which has a 5 nanometer of SSMO sandwich between the two lanthanum nuclide electrode here, what do you see here is that it's a different, this transport data is, this R versus T data is different than these two. What is the difference here is that what you see that the resistance is first increasing weekly, I would say, with the decreasing temperature. Why I'm saying weekly is that you see that resistance is going from 500 to like somewhere 600, 760. Okay, when you decreasing temperature from 300 to 100 Kelvin. So if it is insulator, the resistance increases quite fast. Okay, so what I would say that this is okay, so this is a weekly, I mean, I would say that the resistance is increasing weekly with the decreasing temperature. And then when you go at low temperature below 100 Kelvin, you see the resistance is going down. Okay, and so there is somewhere here it's becoming flat. So how we can explain this? What is happening here? Something interesting is happening. Okay, let's talk about it. Let's try to understand this. So if we try to understand this, let's compare with the magnetic data of a duplicate film which has a 5 nanometer of SSMO. What we see here is that if you compare this R versus T, this is R versus T, the blue one, versus M versus T, M is the red one. Okay, so what you see, the TC, you can see the TC here. The TC is matching with the peak of this R versus T. Okay, so that means it seems that something happening at low temperature is related with the magnetic properties of this barrier. Okay, because it's this is matching with this. And in fact, when you measure the M versus H at 5 Kelvin, we see nice stresses too. So this is a magnetic systems, and there is something related, magnetic like magnetic properties of this barrier is playing a role here. Okay, so now let's understand this. So what is happening is that above the TC, okay, this barrier is just a normal insulator. It's a paramagnetic insulator barrier. So basically we can say it's metal insulator metal. Now, why resistance is increasing weekly with the decreasing temperature? Because what happens is that the barrier height of this is not that much. So there is a thermionic emission is there. Okay, so that means the electron is classically moving from top of the barrier. So this is happening more at room temperature. But when you decrease the temperature, you reduce the thermionic emission. As a result, what is happening? The resistance increases. Weekly with the decreasing temperature. But as soon as you hit the TC, okay, so what happened is that due to the splitting of the conduction band that we discussed few slides back, that there will be different barrier heights for two different directions of spin of electron. So what happened is that due to the splitting of this barrier, the barrier height for, let's say, for example, up spin electron, that will come down. So that means up spin electron can tunnel preferentially or more than the down spin electron. So lower, so if you reduce the temperature further down, this splitting will increase more and more, and you see the more and more of a spin electron will be here. Okay, and so when you hit here, you basically saturate it. So which is basically, you see here, this is some sort of saturation here. Okay, so there is no further split happens, and that's why the resistance will become flat here. Okay, so this is basically the decreasing or lowering of the resistance at low temperature below the TC provide the evidence of spin filtering. Okay, so we fit this data with some sort of model, and from that we get that the spin filtering efficiency that comes in our device is around 75%. Okay. So that's one way. So there are a lot of other, I mean, if you're interested to know more about this, please go and read my papers. We have got several interesting data, and I cannot, I mean, due to the lack of time, I could not put everything here. So if you are interested, you please read the papers. Okay, so other way of explaining this thing, or other way of sort of corroborating this fact, is when you make a quasi-magnetic tunnel junction. So that means instead of having two metallic electrode, now you have one ferromagnetic metal and one normal metal electrode. So that means this ferromagnetic metal will act as a sensor. Okay, now if your ferromagnetic insulator is giving you a spin filter or spin polarized current, then this ferromagnetic metal will accordingly will sense, right? So that way you can also check, you can also say that your this thin barrier is acting as a spin filter. Okay, so when these two layer would be parallel, then you see there a lot of current will pass through, and then you will have a so low resistance state. When these two would be anti-parallel, there will be high resistance state. Okay, and then you can calculate the TMR with that. So for that case, in that case, I have used lanthanum strontium manganese oxide, LSMO. Okay, so which is basically ferromagnetic metal. This is R versus T of LSMO. When you make a tunnel junction, that's how R versus T look like. So again, the lowering of the resistance at low temperature is that indicates that there is some spin filtering is happening. This is dynamic conductance versus voltage curve, which is quasi-parabolic in nature. At low temperature, we see some sort of zero bias anomaly. That could be some sort of kind of scattering is happening at the interface. Okay, so this is. So what happens is that we use LSMO or LCMO as electrode. Okay, so these two are sort of called the half metals. Okay, so typically people when people check their spin polarization, they show the spin polarization on 90%, but that is their ideal clean systems. Okay, the spin polarization matters here, especially when you are talking about tunnel junctions. Okay, so especially we want to make sure that how the spin polarization of these layers at the interface. Okay, because interfacial density of states matters for the tunnel devices. Okay, so to know the spin polarization of our material systems with our with our barrier, we made our own devices. We made our magnetic tunnel junction, conventional magnetic tunnel junction, where we have a STO as a like normal insulator as a barrier, and then we try to optimize with the thickness, with the voltage, and blah blah everything, and then with that we got the maximum TMR is around 220%, and then with the Julius model we can calculate the spin polarization, which comes around 73% in our case. Okay, so taking that as a spin polarization of the electrode, then we also got the TMR data of our quasi-magnetic junction. So this is the quasi-magnetic junction where we have a SSMO 4 to 5 nanometer thin, and there's a STO which is decoupling these two magnetic layers. So you need to have a non-magnetic layer between the two magnetic layers to see the distinct switching of these two layers. And so with that we got around 100 around 15% TMR, and then spin polarization that we got around 49% with that. Okay, so this is basically other way of confirming that they are thin this ferromagnetic insulator manganite barriers that act as a spin filter. Okay, so this is all about Spintronics part, that we can generate the highly spin polarized current using a thin ferromagnetic insulators which act as a basically a spin filter system. Okay, so other is, now let me briefly talk about ferroelectric systems, ferroelectric memories. So we have worked on several ferroelectric systems, FE-RAM, FE-FET. So you please go through the patents that we have filed recently. Okay, so I'll be going a little fast from here onward. Okay, so this is the ferroelectric tunnel junctions. What we see in ferroelectric tunnel junction is that something called the electro resistance, tunneling electro resistance effect. Okay, so if you use the two metals which has a different electron screen length, then what happens is that when you put thin ferromagnetic ferroelectric insulator. So the bound charges of the ferroelectric insulator, they won't be completely compensated by the electrodes, and as a result, depending upon the polarity of this ferroelectric insulators, you may see the two different barrier heights for two different direction of the ferroelectric polarization. Okay, so typically what you do is that you apply the large voltage, you basically switch this ferroelectric in one direction or other, and then that way you have a different barrier heights, and then you apply a small voltage and you can read this. Okay, so FTJ is important because it can give you like you can do very fast read, right, like nanoseconds. It's a low power consumption devices, and it's a non-destructive readout, and one can think of high density data storage with that. Okay, so this is how the okay, so over the last 10 years people have worked on various systems, FTJ systems, ferroelectric channel junctions. So the purpose of that most like the motivation for the people was how to increase the on to off ratio, because if you get the bigger number, you can get the bigger paper, because you saw the number, you saw always they like record like TR effect or on to off ratio. So typically what people do is that they use the bottom electrode as a oxides. You see that they have used SRO, LSMO, lanthanum nickelate, and many other systems like oxides, and then they use a top electrode as a platinum, gold, iron, cobalt, because the metal has a smaller screen length than oxide. So you see the large screen length difference between the two electrodes, and as a result, you see the big on to off ratio, because you see the two different barrier heights, like well separated barrier heights for two different directions of ferroelectric polarization. Okay, so if you compare with the MRAM versus FTJ, MRAM is magnetic tunnel junction based devices basically. So and why FTJ is interesting, just this slide to give you like in terms of the device performance specs. If you see that most of the aspects, this FTJ matches with the MRAM, though the FTJ is like kind of the best data that I have taken from the literatures and from various sources. MRAM, you can see all these things in one device. So it's pretty mature, 15 years of maturity, where people have done a lot of research in industry and academia both. Here you have people haven't done much of the work, it's the new things, but still if you look that it is most of the things it is even better than most of the for the device specs, even it is better than the MRAM. So if you see the write voltage, you need 0.3 to 2 volts. Read voltage is also the same range or even smaller. Okay, and here the endurance is a problem, because you need larger voltage to switch these devices. So you need to find systems where you can switch them at a smaller voltage. And the on to off ratio, this is where MRAM is not great, which is only 2 to 3%, and that's why you cannot make a standalone memory with MRAM as of now, because it's not we don't have large on to off ratio. However, FTJ give you on to off ratio more than 100. Okay, and write energy is also quite small, like 3 orders of smaller than the MRAM. So the two things that one need to work on is that how to improve the endurance and how to reduce the RA. So that means you have to make thin barriers. Okay, so this is what we tried. So how you can achieve? So basically you need a thin barrier, means you need to stabilize the ferroelectricity all the way down to 1 nanometer, even smaller than 1 nanometer, and this is more possible with the new systems, this hafnia based systems. So it seems that the hafnia based systems is better than the perovskite systems in terms of we're talking about compatibility with the CMOS, and from almost all the aspects, like in terms of growth, in terms of silicon integration, you can achieve ferroelectricity all the way down to 1 nanometers. And even recently Saib Salahuddin's group from Berkeley has shown that you can achieve ferroelectricity all the way down to 1 monolayer of zirconium oxide. Okay, so scaling follow the CMOS, you can have a 3D integration because it's ALD compatible. Only the problem is the coercive field, and that can be even can be worked out if you really have some doping and find the right systems. Okay, and in terms of the polarization, is similar to perovskites. Okay, so we have also tried something in this space. What we have done is that we have grown the HGO, zirconia doped hafnium oxide, on LSMO bottom electrode with the STO substrate by pulse layer deposition techniques. Okay, so we have grown, you can see the films that we grow all the way from 18 nanometer to 1 nanometer films, and we see that when you reduce the film thickness below 10 nanometers, then it becomes a rhombohedral phase, and with the large in-plane strain, we could basically, you can see there, this is all exhaled quality data. And with large in-plane strain, we could actually stabilize the ferroticity on the system all the way down to 1 nanometer. Okay, so this is the PFM. Imaging. So what you see here is that the top one is the phase, bottom one is the amplitude. You can switch this 1 nanometer films one way or other by applying the electric field. Okay, so this is to demonstrate that you can switch them by 180 degree, this from one side to the side. Okay, and then we made then we have done some more ferroelectric measurement. So this is with the 2.5 nanometer films, which shows quite robust switching. Okay, and so then we also did some pund measurements to check the ferroelectric polarization that comes around 30 microcoulomb per centimeter squares with the 2.5 nanometer films. And this is the when you do the testing by the radiant testers, ferroelectric testers, and this is done at 10 kilohertz with the 10 nanometer films, and that also shows a decent ferroelectric loop, and with the polarization is around somewhere 15 to 20 microcoulomb per centimeter square. Okay, so then aim is that to make the ferroelectric tunnel junction. Okay, so we have basically put we deposit the platinum, and then we pattern the platinum top electrode. So here you have a LSMO as a bottom electrode. This is a barrier layer, ferroelectric insulator barrier, and this is a top electrode. And then you basically measure, you switch them in one way or other. So we first apply plus minus 3 volt, and then we switch them in one way or other, and then we measure the IV okay, for the 2 states, for one polarization state and another polarization state. And then you can see that the IV where voltage, we cycle the voltage between plus minus 0.6 volts, so which is basically to make sure that you are not switching back these ferroelectric materials when you apply the voltage, read voltage. Okay, so you see this is the off state, this is the off state current, and this is the on state current, and we fit them with the BDR model, and from that we got the barrier height. So there's a large difference in the barrier heights for 2 different direction of ferroelectric polarization. Okay, so we have seen the large on to off ratio. So this is the on to off ratio of the device with the bias voltage. So we see that the on to off ratio is decreasing when you increase the bias voltage. So in fact, if you are around 300 millivolt, you have which is basically a good enough current you get around for the read around this 300 millivolts, and you still see the significant on to off ratio. And so corresponding RA product that we see around 25 kilo ohm micrometer square, which is around 3 order of magnitude smaller than what people have seen. So purpose here is that how to reduce the RA. Okay, and so that can be achieved when you basically make tunnel junction thinner and thinner. So if you can go below 1 nanometers, even 0.5 nanometers, then this can go further down, and then it can compete with the MRAM structure basically. So this is also further to prove that the switching the device that we got, that is related to the ferroelectric properties of the barrier. So this is the ferroelectric amplitude versus voltage of measured by the PFM. So here we see that the switching matches with the resistive switching in the device. So that means the switching that we see in a device, that's related with the ferroelectric switching in the barrier layer. Okay, so these are a few more data. This is with the 1 nanometer, this is the 2.5 nanometer. We see pretty much same sort of behavior. We could switch them, we can fit them with the BDR model, and this is how the resistance or off versus on ratio is with the varying the voltage. Okay, so also what we found that the device size matters. So when you reduce the device size, then what happens that the on to off ratio increases, because what happens is that when you have a smaller device, you can switch them uniformly at a given voltage, and you can also reduce the leakage current basically, and that way you can improve the TR. So this is also better because we want to make smaller devices, very small devices. Recently in Western Digital, we have tried to make 100 nanometer device, and we could show them that we can switch them. Okay, so this was about the ferroelectric tunnel junction. Now let me briefly talk about this ultra-low energy electric field control of magnetisms. That work we have done with the Intel. We published several articles on this. So if you want to know more about this, please read these articles. Okay, so a few slides back, I talked about STT-MRAM. So if you see that with STT-MRAM, you use the current. So it's current-driven device. So energy requirement, energy requirement or energy which you use to flip one bit is around 10 femtojoule. But if you use something called the magnetoelectric concept, where you basically use some magnetoelectric materials, and that give you that enable you a vehicle where you can switch a ferromagnet by electric field. So you can switch so you can basically manipulate the exchange bias, exchange coupling, or you can also switch the ferromagnet system from one to other direction. So if you use that, the energy consumption that comes in the range of autojoule. So you basically reduce the energy consumption by 3 orders of magnitude. Okay, so we have used the multiferroic materials, which is called which is BFO, which has both ferroelectrics and as well as the magnetic ordering, which is basically G-type anti-ferromagnetic systems. And so when you that you can see this at room temperature, both orderings. But what happened is that so when you make a thin film, you see the small canted movement, which is magnetic movement is around 8 mu per cc, which is really small. So people in past our group have demonstrated with Ramesh that if you switch the ferroelectric polarization or ferroelectric domains in these materials, you also see that the anti-ferroelectric domains or anti-ferromagnetic domains also switches. Okay, so this is one-to-one correlation between the anti-ferromagnetic domain and ferroelectric domain, and in fact that was well established by when you put the ferromagnet cobalt iron on the top of the BFO, and then you see there is a one-to-one correlation between the ferroelectric domain of the BFO and the ferromagnetic domain of the cobalt iron. So that means there is strong interactions between the the canted movement of the BFO with the magnetic moments of the cobalt iron, and you can switch them back and forth with the electric field. So this is before polling and this is after polling, so you can basically switch them. So this all was done at higher voltage, 500 volt, 5 volt. So with the thick films, the purpose is that how to reduce the energy. So you want to get the switching at lower voltage, and for that we have to do some engineering. So basically we need to reduce the switch depolarization, you need to reduce the coercive field, and at the same time we need to make sure that we have enough magnetoelectric coupling. And so also we want to make small devices. Okay, so when you do that, a lot of concerns that one has to take care of. So we have done that. We have basically doped the BFO with the lanthanum doped the BFO, reduce the film thickness to 50 nanometer first, and then here we have made some GMR structure, spin bulb structure with the same thickness of the cobalt iron top and bottom. You see there's a split loop. So the bottom cobalt iron has higher coercive field than the top one because it is coupled. It's basically exchange coupled with the LBFO, and then we basically measure the GMR. So this is GMR at minus 2.5 volt when you apply, and when you apply plus 2.5 volt, you basically at 100 offset. If you see, you can switch the device between anti-parallel state to parallel state. And if you have this background field of 100 offset, what you can do that you can switch the device just with the electric field from one state to other state. So here you basically achieve the same GMR percentage by the electric field sweeping between one direction to other direction. Okay, so we have systematically reduced the thickness of this LBFO from 50 to 20 nanometer. It's not as simple as it looks like here, because you have to also look about how this interface engineering, pinning effects, and other things is happening, whether you still have a magnetoelectric coupling when you do the film thickness. So it requires a lot of optimizations. So with that, we reduce the magnetoelectric coupling, magnetoelectric switching voltage all the way down to 500 millivolt. Okay, so we also demonstrated this with the PEAM. Here we have put the thin cobalt iron on the top of this LBFO, 20 meter LBFO, and then we apply the electric field, we plus 500 millivolt, and then we did the XMCD PEAM, and then we apply the minus 500 millivolt. Then you can see that we could switch almost like 70 to 80% of this ferromagnetic domain by applying the electric field across this multiferroic LBFO. Okay, so this is how our journey was, that we started, this is 2014, then we started on 2017, and the switching voltage was around 3.5, and we have achieved all the way down to 500 millivolt, and the aim is the 100 millivolt. We did demonstrate something related, something close to 100 millivolt, but we could not get really nice working devices with that, but up to 500 millivolt, we have nice working devices. Okay, so with this, I would like to summarize my talk. So I have shown that we have discovered the spin filtering effect in ferromagnetic insulating magnetized thin films, and that can be useful for memory application. In the second part of my talk, we have shown that how one can achieve the robust ferroelectricity in HGO all the way down to 1 nanometer, and then we shown the large on-to-off ratio with when we make a 1 nanometer barrier devices, FTG devices, and that we believe that if you do more research, this hardware based FTJ can be useful for non-volatile memory applications. And in the last part of my talk, I discussed that if you engineer the BFO thin films, one can make the ultra low power magnetoelectric non-volatile memories. With that, thank you very much for your kind attention, and please ask me as many as questions you have.
Okay. Thank you so much, Bhagwati, for this wonderful lecture. Really interesting results, very illuminating. Before we take questions, I'd like to request you to stop sharing the screen, and I'd like to request everybody to turn on their camera for a few seconds. And then we will take a good photo. I will wait a few more seconds. People are still coming on the camera. Puspendra, you will take a snapshot, yeah? Yeah, as I said, unfortunately, due to the exams, exam week, we don't have many students today. So people are busy, wrapping up the semester. Also, some professors are not here. Yeah, okay. So we take the photo now. All right, cheers. So cheers. Okay. Okay, so you may kindly switch off the camera, and Bhagwati, you please share your screen for question answer.
Yeah, sure.
Do we have any questions? You may kindly raise hands. Maybe I can begin with. So what is the current state of art? I mean, what is the current maximum storage you can achieve with SSD and let's say hard drive?
Hard drive. So,
Yeah.
so you can make 1 TB hard disk.
No, per square inch.
Oh, per square inch. That I don't have that number in my mind, but I mean it's like you can make. Okay, so there are different numbers. Some of these numbers I keep changing with the time. So at this moment you can make around 20 nanometer CD device with a 50 nanometer pitch. Okay, so that means the device size could be around 20 nanometer CD basically, and then so distance between one device to the device around 50 nanometers. That's the best one can do now.
That is in the SDD or the SSD?
STT.
Okay,
HDD is a different technology. HDD is you are not making I mean these kind of patterning devices. HDD is hard disk drive. You have a disk, magnetic disk, which has a grains which store the data, and then you use the read head for reading the information. So that doesn't matter. Like basically around 5 to 7 nanometers of the grain size that store the information, and that you read by the read head, which is have the MTJ structure.
Yeah, I'm just curious. Like, I mean, the STT.
STT won't work there. Yeah, STT won't work there. STT is only for this MRAM, magnetic random access memory. It's for memory application. In hard disk drive, you just use it as a sensing element. This reading element. This MTJ structure.
Yes. No, that I'm aware. I'm just wondering, like in terms of storage. like
Yeah.
how far we can go, you know, with the Moore's law. So like
So
now, yeah.
eight people have demonstrated 8 GB, 8 gigabyte device, like the chip. 8 GB chip is there. Yeah.
Okay, so I'm talking about actually the hard disk what we buy, the portable hard disk. Now we can buy 4 terabyte, 8 terabyte, which are very handy. So
Oh, yeah,
yeah, so
that is.
yeah. So with the same technology, let's say how far we can I imagine of 100 terabytes?
Yeah, I mean, one can, I think these are keep increasing. So there are two different segments of this one. One is the consumers, like what we use, and one is the enterprise. Enterprise is like Facebook and Google and these ones. They use very big one, like one can also make 100 TB device for them. So it's nothing but what they do is that they use, multiple stacks, okay, multiple stacks, and then you have several read head.
But that's not my question. I know you can make a very big hard drive. That's not the problem. I'm talking about the portable ones. So how many? Because when we are having more and more storage in the same volume, so basically miniaturization is happening. But how much further we can miniaturize with the same technology? You know. So for instance, in front
so
of me,
actually there is no. I got your question now. There is no much miniaturization is required and possible here. What people do is more of engineering now. So engineering means you use the disk, either you use a disk on both sides, or you basically what you do is that how close you can read the informations. So there is no further scope of miniaturization is possible here because you have magnetic grains and you read the information from those grains. And frankly,
so I
yeah,
think,
frankly, like it's not of the major focus for the industry now to miniaturize that because it's more of the enterprise or more of the storage things. So for storage part, we are not like industry doesn't care about the miniaturization because it's like you put somewhere. Who cares how much size it takes, right? Because miniaturization also take a lot of cost and technology. So in that sense, it's more of the how much data you store rather than how small you can make that. So how much data you store in one like device or that disk, that is how it's more of interest.
Yeah, I mean, previously, let's say 13-inch laptop, it was like 256 gigabytes. Now it is possible to buy 1 terabyte. So I'm wondering
so
what
so that the one you're
expect
talking about,
next
one TB, that 1 TB is not HDD, it's not hard disk drive now anymore. It's more all SSD.
Yeah.
None of the new laptop is having a hard disk drive. It's all SSD. It's a different technology. It's a floating gate based things. Yeah.
All
It's a
right.
different one. So there people can thinking now even going to larger than like 1 TB you can find now. It can even you can go to 5 TB. So this is what people are working now is Western Digital also big six and like different technology. You are basically doing now 3D structure. Not instead of 2D, you are doing a 3D. So you use ALD system to grow the 3D structures, 3D NAND. Yeah.
Okay.
That is called 3D NAND.
That was exactly my question. So the
so it's a different. It's not hard disk drive. It's nothing.
No,
I didn't.
That I understand, but because you were in this business for some time, so maybe I thought you can comment like with SSDs also, what more to actually expect, you know? So can with the same small size laptops, can I expect 5 terabytes or 10 terabytes?
You will expect soon, very soon. It's working. Like there are different, like big six, like different technologies coming. So it can go to 10 terabyte actually in few years. Very soon.
That's nice. That's nice. Okay.
Yeah.
I think Andreas has a question. Andreas, please unmute, switch on your camera and ask.
Thank you. Also, thank you for your talk. Yeah, I had a question regarding the first point of the spin filtering. I think the question I have is on the coincidence of the spin filtering onset and the magnetization behavior. I think that was a view graph 24.
Yeah. Here.
Exactly here. So if I were to guess the the Curie temperature from the magnetization data, I would come up with a temperature quite a bit smaller than the peak position that you see in the resistance. And even if it is the TC were the peak position, at that point, your effective magnetization is basically zero. So the difference in the tunnel barrier is basically zero. So that's where you should see an initial start of the deviation from the what you're insulating or semiconducting behavior that you see, but you see the peak there. I don't quite understand how this matches with your explanation.
Yeah, very good question. I like this really. So nobody has asked this question before. I mean, you pointed very right thing here. So what happened is that when you measure the film, okay, so when you measure the film magnetic properties like 5 mm by 5 mm sample, okay, so uniform films. But when you measure the R versus T of the device, there's what you do is that you basically fabricate it, you make a small nano pillars and blah blah blah. So with that, you change the magnetic property as well. You change the magnetic like dimagnetisms will become different, like this shape and isotropy will play a role. And then you see that the TC doesn't match. It's always a little bit here and there. In fact, within the film itself, if you make a small films, like a small part of that, the TC will be a little bit here and there. So TC is not always same, especially when you make devices. And so that is the one reason. Other is that this is more of phase separated systems. So though the TC of the bulk systems that we see is around 100 Kelvin, but it started showing behavior of some metal to insulator transition or percolation started even little higher temperature. Okay, so that is somewhere here around this. So it started even showing that kind of behavior there. So that is what you see. And so also interface play a role. So what is happening at the interface, these tiny informations, that is difficult to know.
But you have any evidence for this percolation behavior?
It's very well known in the magnetite systems. It's very well known in magnetite systems. People have done a lot of study on this like 15-20 years back.
But typical manganites show very conventional scaling behavior.
No, scaling behavior in what sense?
Well, the typical scaling behavior of phase transition.
Now, okay, now let me come to the basic magnetite systems. If you see metal to insulator transition in the magnetites, okay, so what happened? Metal to insulator transition TC should be sharp, but it doesn't go sharp. It also go gradually all the way down to So you see the broader. In fact, it depends upon the film thickness, how the strain is playing. There are various order, like there's a charge, spin, and orbital ordering taking place in this system. So eventually the magnetic in this system is not sort of conventional, is like a different way, like either super exchange or double exchange mechanisms, and which is basically the role of the oxygen orbitals play here a lot. And how much is strain there, what is the angle between the oxygen, this metal or oxygen metal bond, that play important role. And so how they may change with the thickness, with also with the when you make the smaller shape and size. So that all matters a lot. That's why people could publish millions of paper in manganite system, because when you do a little bit here and there, things change dramatically.
Yeah, but what I had seen is that the scaling behavior, yes, the TC switch is quite sensitive, but the scaling behavior not necessarily. But typically, when you take the film and do nanofabrication on things, typically the order temperature would go rather down than up. But to have a consistent explanation here, you would have the order temperature to go up with the nanofabrication. Am I right?
A little bit up. I mean, that you can, but it's not drastically changing also, Yeah. So, yeah.
Okay, thank you.
Yeah, sure. Thank you. Yeah.
Yeah, thank you, Andreas. Thank you, Bhagwati. Are there questions by anybody else? Please raise hands. Okay, I don't see. So I think, Andreas, you want to ask one more question?
Yeah, well, if nobody else asks another question, then you show in the last example that, well, you're aiming at reducing the energy that you need for switching with the ferroelectric effect. And I guess the tendency is very clear.
200 millivolt, yeah.
What is there going to, I mean, if you make it much easier to switch this, aren't you at some point also more susceptible to simple thermal fluctuations?
Yeah, very good question. That's true. So that is 100% true. So when you're talking about 100 millivolt switching devices, you also have that problem that you don't have enough barriers between the two states and whether you have enough stability or not. Yeah, this is right question, and probably we don't have the answer of this right now. So because it has not been realized yet. And that is always the question in all sort of devices, not only this. Even in MRAM, we talk about, in ferroelectric RAM, we talk about, we want to make sure that your delta has to be enough. This delta need to be enough so that you can have a retention. And that's always a tricky point, that how much switching voltage you need, even for read. If you have a switching voltage is small, reading is already an issue also, because you already switching voltage is so small, and then you have to read even a smaller voltage. Okay, and so whether you get the enough current while you do the read, and also when you do that read, you need to make sure that you don't do back flipping. Okay, so and that time the temperature thermal fluctuation. So it's I would say it's art to find that right balance. Whether 100 millivolt is right or not, we don't know. Maybe it's not right, or maybe it's correct, but that need, with the technology, we will understand that. Yeah, but that's very valid question. Yeah.
Thank you.
Okay, Puspendra, you want to ask a question?
Listen.
Yeah, I think you wrote a question. Why don't you read it?
Yeah, I see that. He asked the question that you mentioned you have used nitrous oxide for LSMO growth. Typically, people use oxide. Yeah, good. That's really good that you really pay attention on that thing. Though I did not discuss that. So the reason is that okay, I tried oxide. And somehow the things didn't work out for me, because the reason is that you are growing here heterostructure. You grow lanthanum nickelate, then you have to grow SSMO, then you have to grow lanthanum nickelate. So I have to grow multi-layers here. So what I found that lanthanum nickelate need much higher oxidation pressure, okay, to get the good metallic films. However, SSMO and these things need less oxidation pressure. So eventually I could not get that much of oxygen pressure or oxygen, atmosphere for lanthanum nickelate growth. So what I found that if you use the nitrous oxide, which is more oxidizing, okay, and it oxidizes it faster and better. So then I could grow, because I cannot use nitrous oxide only for lanthanum nickelate and oxygen for LSMO. Then it will become a little different. So, but I could grow all of them in nitrous oxide. So it did work for me. But that's how yeah. It's a different recipe.
But sir, then nitrogen of this nitrous oxide is not creating any trouble during the growth of LSMO or SSMO?
I don't think so. Nitrogen, like where nitrogen will sit in oxide systems. Yeah. So typically people grow like, in this the superconducting stuff, where people need different oxygen pressures and oxidizing things. People use this nitrous oxide a lot. So yeah.
Okay, thank you, sir.
Okay, so I think it's about time. There may be more questions, but you can write to Bhagwati. I'm sure you will clarify that. So Bhagwati, if you stop sharing, I like to share my screen to present a small token of appreciation. Do you see my screen?
Yeah, I see. Thank you. Yeah.
Yeah. So on behalf of our W2S team, I like to present this small token of appreciation. Of course, we would love to have you in the campus sometime soon, and
Sure.
then have some personal interaction. So I will read it. W2S seminar webinar series on Spintronics, NICER, Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Bhagwati Prasad from Indian Institute of Science, Bangalore. in recognition and appreciation for being a valuable speaker to give a lecture on Beyond-CMOS computing, Spintronics, Ferroelectrics, and Magnetoelectrics. So thank you so much, Bhagwati. Really very kind of you for joining our seminar program. I hope you join the future seminars too.
Sure,
and thank you all for joining, and see you next week, same time, same day. So until then, have a good night or good day, wherever you are, and have a nice day.
Bye. Thank you.
Bye.
Bye.
Bye.